everyone for joining us today. I see that we have about just under half the people who have registered online already, and I know that some aren't able to make it due to parent-teacher interviews and other things. So welcome to all of you. I'm just going to share my screen and we'll continue forward. So welcome to the Queensland Bridge Competition Teacher Information Webinar. You notice, for those of you who have participated in this competition in the past, I've actually changed the name a little bit. So instead of being the Spaghetti Bridge Competition, we're just making it the 2024 Queensland Bridge Competition. There's a little bit of a funny story as to why the name has changed slightly, and I might share that with you later if time permits. But it's more about the fact that we're also working this in New South Wales now, which is really cool. As we are meeting together, we would like to acknowledge the Turrbal, Yagara and Gobi Gobi people who are on the lands of which Mike, Hinu and I are, and also the lands on which you are currently sitting all across Queensland as our First Nations owners. We pay respect to their elders, laws, customs, and we recognise their contribution to us as a society and to engineering in particular. So who am I? For those who haven't had any introduction, any interaction with us in the past, I'll introduce myself shortly, but the Engineering Link Group is a small organisation of two people who we started working together in 1994, two schools up in Townsville. I was at Darrengower State High School and my colleague Paul was at Townsville State High School. And this began way back then. So this is our 30th year of operation, which we're pretty excited about. It also shows in the fact that you can see almost no hair left on my head. The whole purpose of why we started is because as a high school teacher myself, just coming straight out of university, I couldn't really answer the question, why do we teach what we teach in any sort of great depth or any great detail. So we were looking for ways to help support teachers, and engineering was that brilliant path. We, as I mentioned briefly, but now COVID is over, we're back to running events all the way across the eastern seaboard. So we have multiple events here in Queensland. We're also in New South Wales and back in Victoria for the first time for a number of years this year, which is very exciting. So who am I? Pardon me. My name, as I said, is Greg Millican. I've been teaching for way longer than I want to admit. My current role is I'm head of curriculum leader of mathematics here at a little BCE school in Burpengary, North Brisbane. But previous to that, I was a CL for science and maths here. And then before that, I was head of mathematics at Townsville State High School. As I mentioned, Paul and I formed the Engineering Link Group back in '94. Paul is now retired from teaching, but is still active as much as his health allows in our events, which is really exciting for us. The Spaghetti Bridge Competition, or the Queensland Bridge Competition, has been running under our auspices since 2014. It was given to us by TEAS. They went in a different direction and asked if we wanted to take it up, which we did, and we've been supported by the Queensland Government, specifically through the Department of Transport and Main Roads, since we took over in 2014, and we're very excited for that partnership to continue beyond this year. And also Engineers Australia, who also support us across all of our events here in Queensland, and we're very grateful to both of those organisations for continuing to support us. So today, I'm going to hand over shortly to Mike, who has very kindly donated his time. This is, I think, the 4th or 5th year that he's donated his time this afternoon to talk to us about engineering and bridges, and I'll let him introduce himself shortly. But Mike is the senior engineer at the Department of Transport and Main Roads. And then once Mike has finished, and he has lots of great tips and ideas about bridges, but also bridges built out of spaghetti, which is obviously not something he does on a day-to-day basis, but having been involved in this competition for a while now is quite an expert. And then I'll have a chat about the competition itself. So I will hand over to Mike. Let's stop this and he can take it over. And then we can move from there. I will mute myself, Mike, and let you get.
All right, I'll see what I can do with my share. That screen there, hopefully that's come up. Is that working?
Yep, I've got it here. Yep.
That's all right. It's disappeared off my screen for some reason. All right. Well, good afternoon, everyone. Yes, my name's Mike Whitehead. I'm a director at Transport and Main Roads in our structures area. And I've, like Greg, I've been working probably longer than I'd want to remember. And I've been delivering this session on the basics of bridges now for a number of years to help out there. And yes, a large scale bridge like the Story Bridge or the Gateway Bridge or anything like that, all basically is very similar to what our students have to do and understand in doing a spaghetti bridge. It's a little bit simpler, obviously. So what I intend to do is just really go through the fundamentals, the basics, to hopefully give you a bit of an insight on how to guide the students, point them in the right direction in learning about how things occur in a bridge, what's important, and then even experimentation to work out what might be better than the other. So I'll get underway. And so, sorry that I've got the names around because I still call it the Spaghetti Bridge. But anyway, again, I'd like to acknowledge the traditional owners and elders as well. Briefly, what I'm going to cover today is look at forces. It's probably the critical component of a bridge. It's the basics, the physics of a bridge. And so the stuff that the students are learning in school will be able to see it here in action in a bridge. We'll then look at the types of bridges. There's not just one, there's quite many, and they all have their strengths and weaknesses. And then we'll have a look at a bit of the practical application of that knowledge in terms of this project in development of a spaghetti bridge. So moving forward there's a picture of the rail bridge over the Brisbane River. That's an arch bridge, and even just students looking at pictures of bridges like that can give them some ideas and some thoughts about maybe what they would like to try and emulate or use or copy. So essentially, when considering a bridge, we must first understand what forces are involved. And the reason for that is that a bridge carries those forces. It's got to deal with those forces. Now, forces can be static or dynamic. Static is stationary. Dynamic is obviously it's moving. So in a road bridge, cars moving across the bridge is a dynamic load. Wind can be a dynamic load and things like that. For our project, we really only need to look at static. Yes, it's going to have a load that's going to be cranked up and increased, but it's located in one location. It doesn't move. So it's a static project. The bridge itself is a structure. It consists of many components, and what it has to do is support itself. So the weight of the spaghetti has to obviously, and the hook that's on it, that all has to be supported, and that's what's called a dead load. Then it's the live load, which is the load that it carries. In this case, it's going to be located at the center and pulling the bridge down to work out how strong the structure is. What the spaghetti bridge is doing is actually transferring that load, that live load, through itself to the supports on either side, and that's what it can carry. When it can no longer carry that or transfer those loads, that's when it fails and breaks. So there's a number of forces, and this is where we get into the good old physics. So obviously a piece of spaghetti can be under compression. Now, whether it's a piece of steel, piece of concrete, piece of spaghetti, whatever it is, if you have forces either end of it pushing it in to try and squash it, it is in compression. If you grab it and try and pull it apart, that's tension. You then can have bending. So again, usually if you put like a ruler on two rubbers on either side and try and bend it in the middle, that's a bending motion. There's a shear forces in it where one part of it wants to go one direction, another part goes in another direction. That's where it will snap. And then you can obviously twist it, and that's what's caused the torsional forces. Now, interesting enough, all of those will be present in a spaghetti bridge. And so the students have to sort of understand that and design and fabricate or build their bridge to handle these forces. And I'm hoping to give you some guidance on that. So obviously when a member is under compression, so you try and get a piece of spaghetti and squeeze it from both ends, it'll try and buckle. It's going to bend in, out, whatever it is. So that's the failure method. So obviously if you squeeze it too much, it will just bend too much and then break itself. So when you've got pieces that are under compression forces, you try to thicken them up. The thicker they are, the less likely they are wanting to buckle. Under tension, obviously when you try and stretch it, it's ultimately going to snap. It's just going to start getting thinner and thinner when it starts to fail. Spaghetti, unfortunately, doesn't really thin down. It just breaks. So it's a bit hard to work out if it's starting to fail there. Not much you can do about it other than, yes, thicken the member up, but generally you find members under compression are thicker than members under tension. They usually can tolerate more force and therefore can be thinner. When bending occurs, you actually have multiple forces occurring in the structure, and there's different ways to handle that bending, and that's why we have different shapes in our bridges to handle that. So let's expand that a little bit more. So here's essentially a beam across two supports, and we load P is in the middle there. This is kind of what the spaghetti bridge setup is all about. So the bridge itself, or the beam in this case here, is actually bending. So you can see it physically bending. The two supports are pushing up. That's RA, RB. They're not moving, but they're holding the structure up. So they're upward forces, and P is a load. It's pushing down. So you'll get that bending type of force. If we have a look at it a little bit closely, the top part of this beam is actually trying to shorten. So when it's bending down, it's actually shortening. So it's in compression, where alternatively the bottom side of it is actually trying to stretch. So therefore it's in tension. So a beam under a load and bending load, is actually experiencing compression and tension at exactly the same time. So again, the structure has to be able to cater for that. You'll also find that there's shear occurring. It's usually towards the ends. So again, it's a spot placed between the forces. So you've got P down and the two RAs up. So shear is going to go somewhere in there. And it's usually closer to the supports that they will go. And that then again, to cater for that, maybe a little bit of thickening around that area to cater for it. And the other one that's there is obviously torsion. So under load, for various reasons, unless it's perfectly symmetrical, any little offset, even by a mil or two, the beam or the member will start to want to twist under extreme load, and that's where the torsional twisting starts to cater for it. And again, there's ways to compensate for it that we use in our day-to-day structures. So again, simply now we have two supports, which is the frame that the students will load their bridge on. The red represents the spaghetti bridge, whatever shape. Then there's applied load underneath it, which is on a hook, and it'll be pulling down. So roughly speaking, the load will split halfway, and it's probably really important that students understand this. To even up the structure, try and get the when they're setting it up on the rig and when they're actually building their structure, try and get the hook right in the middle so that you do get as close to possible as 50% of load going to one side and 50% load going to the other. If it's off, you're starting to increase the percentage of load going to one side than the other. So that side will be the side that's going to experience the most loading and likely to be the failure point. So you want the whole structure to basically try and share the load as roughly as you can, as close as you can to half-half. And then how these loads are transferred does depend on the type of bridge, which is what we'll explore now. So there's a whole range of structures around the world, and this doesn't cover all of them, but this is probably the main ones you'll see. So a beam bridge is quite a common one. It's just simply a whole series of beams with a deck on top supported by the piers underneath. Then you have a truss bridge, which is essentially they can get a longer structure or a longer span because the loads are transferred from the deck up through the truss and then transferred across to the other side. Cantilever bridges are a little bit unique in the sense that they self-support from one side and self-support from support from the other side. So essentially, you can see a little gap in there. It means that the bridge doesn't actually have to connect. If you take a cantilever bridge like the Story Bridge and cut it perfectly in half, it won't fall down because it's supported by the two main supports and the span is held up evenly by either side. So it doesn't rely on sharing load across. You have arch bridges, and I showed you a picture of an arch bridge, and arch bridges were some of the earliest bridges ever known to mankind, built with stone in the shape of an arch over creeks, etc. So they're a very strong structure. Then you have suspension bridges, and that's a whole new ball game, and then cable stayed bridges. Again, the picture that was behind me was on the left-hand side of my head is a large cable stay bridge. All right, so the ones that you're most likely to come across in this competition is a beam, of various shapes and sizes. Trusses do appear occasionally. The one that seems to be the winner at the moment is an arch bridge. Unfortunately, this picture is not valid because you can't use the sides of supports, but you can flip it and put the arch above, and that's the type of structure. Very difficult to make, can be problematic, but it also at this moment in time seems to be one of the stronger structures. I think it's probably because people haven't considered trusses and beams probably more fully, and these ones would be easier to build than the arch one. But yeah, we'll see, and it's up to the students to maybe try a few of them and see which ones they like or which ones can work better for them. So now looking at the practical application. So again, what we're looking at is these bridges are basically using commercially available spaghetti. Go to the shop, buy it. You're using simple either PVA, white glue, hot glue, or super glue. The dimensions must include a loading hook at the midpoint of the bridge. You must have a deck. I won't spend too much time on this because Greg goes through it a little bit more. The important thing about the deck is you must actually have a deck on it. It only needs to be about 3 centimeters wide. Doesn't have to be very wide. It's essentially we can drive a matchbox car across it. Now, it doesn't have to be continuous. You can have little gaps, so you can have spaghetti, a little gap, another piece of spaghetti, another little gap. It's to look like the deck is there, but you don't really need to have one. It must have a span of at least 35 centimeters. That's what's between the supports. And of course, there is a mass limit on it, which is the real challenge to try and get as close as you can to 300 grams without going over. So the key factor to understand how the spaghetti performs. So how's it going to perform under compression, under tension? When it's glued, does it actually change properly when it gets wetted up with glue? And to make arches and some other shapes, we've had students slightly wet or dampen the spaghetti so they can actually then bend it into shape and then let it dry. Does it change properties? Again, it's essentially flour and water, etc. So does it actually change? And students could actually undertake this through a series of little experiments whenever time can permit to just see how it works. So it is important to try and test and prototype your designs, and so probably getting students started earlier and have a bit of a play. Maybe there's probably a ton of them on YouTube. They could get some ideas from there and see how things have worked from there. And let's also note that the quality of spaghetti does vary from brand to brand and from packet to packet. So it's not a consistent product. So there's no real easy answer which brand's better than another brand, and you could get a dud packet that breaks really easy. So it's probably just use what they can get. All right, how the metal hook is supported is probably a key point because the load is applied to there. So it's a real concentrated point force, and it's going to try and pull the bridge down. And so how the metal hook is placed in the bridge and supported is really, really important, because the spaghetti, if it's lightly supported in there, the load will just break the spaghetti pretty quickly and fall through, and the rest of the bridge will stay still. So it is really important to keep that area, to keep it well supported, well braced, I suppose, in the structure. As I said, the deck doesn't need to carry any load, so keep it light. And it is important to brace the structure, and we'll get a little bit more into that. The bracing actually stops the twisting. All right, so let's have a look at some truss bridges. There are several different types of trusses. The common ones are what's called a Pratt truss and a Warren truss. There's the pictures of them, so you can see a bit of the difference. What we've shown you there is with a load at the center, which simulates what we're doing for a spaghetti bridge, you can see which members are in tension, which members are in compression. So again, having a look at that, we know that the buckling is probably the failure mode in compression. So maybe those members are a little bit thicker than the members in tension. So again, it might be to positively think about how we can distribute the load to maximize the strength of it. What we can do then is instead of making all members exactly the same, you could be wasting material. This is a fully detailed type picture of what a truss bridge looks like. This one here, obviously you've got a truss on one side, another truss on the other side. You have a deck that's there, and then you actually have all the different cross braces in there to stop it from twisting and moving. So the students wouldn't have to build something this elaborate, but it would certainly give them some good ideas how that they could consider, how they could brace it, etc., and actually make a box shape which is quite a strong shape to carry the load instead of having like one truss. There's an example of a great truss bridge, similar to the one I've just drawn or shown you, which is the Burdekin Bridge up in North Queensland. It's been there for quite a long time, carries both road and rail, and that is a really good example of a good truss bridge. So next one we've got is arch. So arches are, as I said, quite a strong structure. So the top arch is actually what carries the majority of the load. So whatever's on the deck, or the stiffening girder as it's mentioned here, basically that load gets transferred up through the hangers into the arch, then the arch then transfers that across to the bearing supports on either side. So the arch itself is usually quite a thick, strong structure. With spaghetti, as I said, typically you would have to wet it up or make a bit of a jig for it, wet it up and then lay it in there and let it dry, or glue it in so that it dries in that arched form. And then you'd have to put in the hangers down to your deck. If I go to the next slide, I think it is. Yeah, on the right-hand side is a bit of an example of some arches that have been done around the world in spaghetti bridges. This one doesn't really have a deck, so it wouldn't pass. And to improve the strength, all the hangers are coming down to where the hook is. So again, the students could do that. We've had examples of that in the past here in our local competition, where the hangers all come down to where the hook is to try and transfer all the weight or the force on the hook up into the arch and then down to the sides. But again, as I said, this one doesn't have a deck, so it wouldn't pass and wouldn't be permitted. And that's the picture I showed you. Those hangers obviously are looking at multiple locations across the structure, across the deck area, to transfer those loads up into the arch. Beam bridges are probably a little bit underrated, but they're very, very common and can do a very good job. So beams or girders need to be quite thick or deep enough to resist the bending forces. Now you can demonstrate a beam bridge quite simply to students. As I said, get a ruler, 30-centimetre ruler, put a rubber under either side. Put it on a flat side down, and then if you press on it in the middle, it'll bend very, very easily because it's not very deep. It's not very thick in the direction of the force. But if you turn it up on its sides and then put your finger in the middle and try and bend it, it won't bend because the thickness is now several times larger. And so that's what you're trying to do in a spaghetti bridge, is get your beams that don't have to be very wide, but they'd have to be quite deep to try and give you that bending moment stress, to resist the bending moments and not move so much and carry the loads. The problem is they'll twist easy. So that's where having two side by side with some bracing will benefit. Just a bit of a stick diagram, or arched impression of a bridge. And you can see here we do have the cross bracing that goes across between them in real structures to help stop that twisting motion. There's a number of different beam types. So you have solid beams, you have I girder beams, T girder beams, and box beams, and there are several others. My animation didn't work on this, so I don't really know what's happened there. But anyway, so looking at, say, a solid beam and making one in spaghetti. So you'd make a little jig, but essentially what you do is you just layer the spaghetti inside itself like that until you get the shape you want. Now, obviously, the depth, as I said, improves the strength against bending, which is your predominant force that you're going to deal with. The width will resist the twisting, but if you put another one beside it and put some bracing in, then that can help with the twisting. The other ones that are there is the common variants are I's and T's, as we mentioned before. The benefit of having like an I, as I mentioned to you before at the beginning, with the different forces, the top flange, or the top part of the I, and in this case the T beside it, that is in compression, and so it's going to want to move and buckle, so you can thicken it by putting that top little flange on it. The bottom is in tension, and so if you need more force there, you can use the bottom part of the I to give you that extra strength at the bottom where the stresses are the highest. You can then thin down, I suppose, the link between the two, because that is just holding the bending moment. So you can make it thinner. So that's where I's and T shapes do come into existence, to look at those different forces within the member itself. So you've got those. And these are the typical bridges that you'll see around Queensland and the other states, where the the beams are just made, and they put them onto the headstocks and the piers, and then the deck is part of it. And yeah, they're very quick to build. They do a great job. Another example, just looking up under one of these bridges, so you can see a whole range of these beams. They're like an I-beam, I believe, but the top flange is much wider than the bottom flange, which is fine. You can also note the cross bracing between them there. Again, that's to help stop the twisting. We talked about the box beams. So the Gateway Bridge is an example of the box beam. A lot of people think that that big sort of shaped arch box underneath the bridge is solid. It's not. It's actually a hollow box, and you can walk across the bridge inside that. I haven't had the pleasure of being there, but I've had colleagues who have. There's various shapes there you can see for different widths required, so you can taper them, make them a trapezoidal cell, or for simplicity of building, you can potentially just have a single rectangular cell. I've got a feeling that a well-built box beam would probably do well in this project. One of these days I might actually try and make one myself and see how it goes. Just to finish off, this is a bit of not a unique picture, but this is a combination bridge, not something for spaghetti. It's an old timber bridge which has had some bracing put on it to help to keep its strength up. Then you've got the different spans in there, including having a steel truss across there, open truss. And that's it from me. I will hand back to Greg.
Sorry, whoops, sharing the wrong page. There we go. So thank you very much, Mike, much appreciated. As always, and I think that's the fourth or fifth time I've listened, and I learn something new every time, so I really appreciate your time, mate. Thank you for that. Just something I forgot to mention at the start for those of you who have just joined us, you might notice that there's a chat, the chat function's open. So if you have any questions, either of just what you heard from Mike and you want to jot them down before you forgot, please do so in the chat. We'll, at the end of the presentation, I'll go back through the chat, and either Mike, if they're addressed to him, or I will answer those as best we can. And once we've addressed all of those, then if anyone has any additional questions, we'll feel free to either put them in the chat or unmute yourself and go from there. Okay, so I'm just going to talk specifically about the competition and some other areas about it and what you can do, and some support that we have in order for you to participate. So the competition's open for all students from grades 5 to 12. So I know some of the participants in the webinar are from our primary school, so you're most welcome. You're also, if you're in a high school and you like to do outreach to your feeder primary schools, this might be a great way to bring them on board and have a STEM competition across your campuses. You can have teams of up to 4 students. As Mike mentioned, it's store-bought spaghetti and glue. I'll go into a bit more detail in a moment. We test it on a rig, and whichever bridge supports the largest peak load before it fails is declared the winner, and I'll explain that in more detail shortly. It is free to enter thanks to the Department of Transport and Main Roads in Engineers Australia. We can if you have only like individual students who want to enter, that's not a problem at all. Last year's winner did it by himself. The student who came second did it by herself, and so forth. So that's not a problem at all. I'll talk about where we're testing in a moment, and it's open now. So the competition's open as we speak, and I'll talk about that as well. So a few of the rules, just a few. As Mike mentioned, the rigs that we have, and I have 2, you can see one in the small photo there, which is the big one. And I have a small portable one, which I use to take around. They have a span of 35, so the inside dimensions of the rig is 35 centimetres. So you need the bridge to be longer than that, so it can sit comfortably on there. So we'd like to say at least 37 centimetres, but that only gives you a centimetre at each end, so a bit longer than that. No longer than 50 centimetres, just so it fits properly on the rig. But it can be as, you don't want to be too long because that's wasting spaghetti. As Mike said, we want it to be at least 3 centimetres wide to simulate that idea of having a deck. Mike talked about the idea that the bridges can't touch the sides, and that's true. So if the students can build a bridge that goes downwards from the top of from the surface of the rig, but as soon as it touches the sides, so if it starts to break apart and touch the sides of the rig, then at that moment it's deemed to be failed. And one really key point is the bridge must be no more than 300 grams. Now, if your students present a bridge that they can't adjust and it is more than 300 grams, then we will still test it, of course. We will still go through the process, showing them, put it on the rig, getting them to test it and so forth, but they won't be eligible for any prizes. Now, that 300 grams includes the load hook. Now, the load hook is provided by us. If you've put in an expression of interest, then you should have a load hook already. If you've done your expression of interest in the last week or so, then those load hooks are in the post. I posted them yesterday. Once you have an idea of how many load hooks you need for your school, then I'll send a contact email out in the next couple of weeks for you to start to think about if you need any more than that. The load hook doesn't have to be secured into the student's bridge. It can be moved from one bridge to another. It depends on how your students decide to build their bridge. That's an example of a bridge from a few years ago. You can see a picture of the load hook and the span. That's 35 centimetres. That bridge has yeah, mate.
Greg, are you supposed to be sharing your screen?
Oh, am I not sharing? That
No.
doesn't help. That doesn't help. Thank you, Mike, for pulling that up to me.
I just realised it.
Let me try that again. I appreciate you letting me know. Let's try that again. Is that working now?
Yep.
Beautiful. Thank you, mate. So I'll go back a little bit. So yeah, so that it was just those pictures. They weren't very exciting. So this is the first one where you really need to see it. So you can, and so this is an example of what the load hook looks like from top view, bottom view. The eye there needs to hang down, and I can give you some dimensions. As you can see, they're around about 67 grams. They're custom made for us, so they do change. The mass changes slightly, but not significantly, and that's the approximate size of the plate. So 30 mil by 75 mil. So the 30 mil, you can see that if they choose to put it lengthways along their bridge, that's where the 3 centimeters comes from. So it has to be at least as wide as the load hook plate. Any brand of spaghetti is fine. We don't care. We're not precious. You can have home brand all the way through to the most expensive spaghetti. It depends on what they want to use. But when it comes to the actual spaghetti itself, as long as it's called spaghetti, or sometimes, as you can see from the Zaffarelli brand, they number their spaghetti sizes. So size 4 or size 5 is fine. Angel hair is way too thin, and they won't want to use that anyway because it'd be night. So the types of glues that we're allowed, so you can use PVA glue if they choose. We had a student a number of years ago do some experiments across different types of glues, and this is what he found. PVA is quite slow to dry, but it is strong. It also fills up in gaps, so that's a good thing, but the slow drying is a bit of a negative. Hot glue dries really quickly, as you've ever used it, but it's not very strong in terms of its bond. It also fills in voids in the spaghetti, being a natural product. Super glue is probably the best of both worlds, although as anybody who's ever worked with super glue, it's a pain. So that's an issue. A couple of things that you're not allowed to use. You can't use epoxy or 2-pack, and you can't use liquid nails either in that form in the tube or in the gun. None of those are allowed this year. Made a bit of a change from last year. So where to start? Well, Mike's gone through a number of different designs and he's given some his ideas, and I'd still love to see a box beam as well. I think that would be really interesting. So as a group, it'll obviously depend on how much time your students have and how much time you're willing to donate to them. But I'll show you some past bridges in a moment and where you can go to have a look at those. Try some different glues, see which works best for you. I know of a couple of schools in our area that have already built some bridges and done some testing, and then are going to go, and so they can narrow down their ideas to the best ones. Build the bridge in sections. Don't try and build it all at once, and then combine them together. And as Mike said, it is so important that the load hook is as centered as possible and the bridge is as balanced as possible. So the structure is even on both sides. Otherwise, one side will take more load than the other and it will fail more quickly. I've included some links here, which you'll get a copy of this presentation in a couple of days' time. So you're welcome to just use those links. Some of you will know other links to do some designs and some testing. So feel free to use anything you want. These are just ones that we've seen in the past. You can obviously build prototypes if you have the time. Some things to consider when you're building your bridge. This is spaghetti shrinks when it's dried, so keep that in mind. So if you wet it and then dry it, it actually goes smaller than what it was. Try to get it to dry evenly, hence the use of the fan in the background there, the heater, to keep it all evenly drying. Use spaghetti from the same packet when possible. Most spaghetti packets are 500 grams, so a 300 gram bridge you should have enough in one packet. But keep the spaghetti with the bridge when you're storing it, so they're in the same atmospheric conditions. It sounds like a simple thing, but it's actually really quite important. And as you said, where you're building it makes a difference. This is just an example of like putting the length together to make it thicker, but unfortunately this is a photo from quite a number of years ago, and that type of bridge, that type of spaghetti, sorry, it's not actually spaghetti, is not allowed because it's hollow. A few other things to consider: make sure the bridge is longer than 35 centimetres and that the feet are as level as they can possibly be and as rigid as they can possibly be. Even if a bridge is sort of twisted, that's as soon as you see a bridge that's twisted, you know it's going to fail quickly because the forces are not going to be evenly distributed. As mentioned already, please don't use too much glue. We've had some students just paint it in glue. They can be disqualified if we consider the glue to be excessive, but we'll do our best to keep every bridge in the competition. That's the intent. The intent is for the kids to actually be involved, but sometimes we have to draw a line somewhere. So how does it all work? So the winch pulls down on the bridge. That's important for the students to understand. This is a situation where I haven't, in the photo, the winch is that little, so the load cell is in that yellow circle. It weighs around about 0.6 of a kilo, so just keep that in mind. So what I tend to do is if I hook it up and it fails immediately, then we'll give them a small mass lower than 0.6 kilos, and then we weigh it we test it from that point on. The way we measure it is you'll see the winch there. So it'll be the load cell will be attached to the bottom of the hook, and we'll pull down on the bridge using the winch. And we'll continue to pull until it fails. And I'll show you some videos of the tests in a moment. Pardon me. And the load cell has a meter that measures the peak load. So it'll continue to increase until no more load is accepted and the bridge starts to fail away. And then we'll record that value. So here's some examples. I hope the sound isn't terrible. Apologies if it comes through very loudly. Oh, I've turned it off. So this is an example of a test from a number of years ago. Notice, so that's how it is tested. Here's another example of a test. This one is not, wouldn't be accepted this year because the deck is really quite low. But again, you'll see, so we record every test. So this is an example of students having the bridge tested. So the students test it themselves. We record it, and there's an example of the hook pulling through the deck without actually impacting the bridge itself, which is quite disappointing for the kids. But it's good one to show them to what not to do. As I said, we record each test, and then you will get a copy of each recording. So each bridge will get a photo and a recording. This is another one we did up in the Sunshine Coast a couple of years ago. So again, this one. So they just tested. This one goes a bit slow. Apologies, takes a while. But you can just see, you can start to see how it's starting to collapse. So it would have already recorded the peak load, but we'll keep testing it anyway until such time as, and then off they go until such time as she fails. Now this bridge was in 2020. This bridge was the winner, but it would not be accepted these days because, as you notice, it doesn't actually have a solid deck. It's just an open space. But again, I thought I'd show you just for for the sake of it. This one takes a while for it to actually break, and you'll see the values that this bridge was able to hold in a moment. You can also see Mike in the background. There we go. So she takes off. So you can imagine the forces if it's going to explode that much. Let's have a look at the next one. So this is 2021, similar situation. We changed the rules at the end of 2021. So it's winding. Again, it takes a while. You don't see anything on the scales, obviously, but I just want to show you. So that one failed in a different way. And again, the beauty of us recording these is twofold. One, it's good for this sort of thing and you can learn from it. But two, the students who built it can take it away and try and analyse and see why it failed and where it failed to improve. And the reason I say that is because just if I go back here, the student in this video and the student in this video and the student in this video is all the same student. So it's the same person, all right, and they won it 3 years in a row because they continue to develop their design. Now, you can't see the deck on this one, but this is the year that we changed it, and it actually has a deck. But it's the same person, or the same group. So again, and she explodes in a fairly spectacular way. Now, this is last year's winner. You'll see the Dodgy Brothers portable rig that I put together. It's a little bit better than that now. So this is the student who won last year, and this is his bridge. And again, he gets up to some serious masses to the point where it actually almost breaks my test rig. See, and there she goes. All right, so here's some results just to give you some idea of the sort of levels that students get to. Not just the high point, but also you notice that even down to 10th place, we're starting to get into realms for those students who are new and those schools who are new. A lot of these, like this was the first year of some of these schools ever participating, and they've done quite well. So don't think that it's just because you're new, your kids are out of this. 2020's results, 2021 results, this is the top 10s, and 2022. So you notice that the name at the top, Chaktastic. So that student didn't win the last year because he graduated year 12. But then last year we have 64. We had a number of good results last year, which is exciting. So again, very grateful to the Queensland Government through the Department of Transport and Main Roads for our prize money. So the first place team gets $700 as the winning prize. Second place is $400 and third place is $300. And then we do location winners. So if you're not one of the first three, but you happen to be the highest achieving bridge in your location, then you will receive $150 for the team. There are some conditions and rules about that, and that can be read in our rules and conditions download from our website. So that's pretty exciting. I know the kids really enjoy getting that cash. As I mentioned, the registrations are currently open. We've secured the 2 places so far, and we're just working with Rocky and school down in Logan and also in Townsville, and we'll get those dates to you as soon as possible, but they will be after August the 13th, so it'll be the week after that or the week after that again. August the 12th, for those who are here in Brisbane, is the public holiday for ECA for the Moreton Bay Logan region, and then the 13th is the day after that, obviously here at my school. Now, if you're not able to make it to one of the testing locations, please don't make that a reason to not participate. We would really encourage you to do so. We've had many bridges posted to us and been successful. So pack them up carefully. We can provide some advice around that, and then we will test them. I will test them for you. We will record those results and you will still see those. If you are around or would like to watch the testing done at Brisbane on August the 12th and you'd like to watch those, you're welcome to tune into our webinar link. Just send me, we live streamed that test day, and you're welcome to grab the link from us if you're interested. So what we had started last year, which we're very excited about, is that Engineers Australia have got some engineers who are more than happy to mentor schools. So we had a couple, we trialled it last year with a couple of engineers and St Aidan's College here in Brisbane. The engineers went out and visited the girls a couple of times in their build up to the testing. It was the first time they participated. Feedback was brilliant from both the engineers and the students and the teacher. So if that's something that you might be interested in, please drop me a line, let me know. I will work through Engineers Australia. We'll work through all the preliminary information, and then we'll put that engineer we'll put an engineer in touch with you. It might be that they come out to school, or it might be that they jump on a Teams meeting like we are now and have a conversation with your students and have a chat to them through their ideas, and the kids can show them what they've done. Whatever works for you, and also whatever works for the engineer and what they have time to do. So if you're interested in something like that, please get in touch with me. I'll make a note of you, and then as soon as we can get our engineers sorted, I'll get back in touch with you and we go from there. So what to do now for those who haven't already, it's live on our website. Pardon me. Feel free to jump on our website, read all the information that you want, that you need. Drop us a line if you have any questions at all. If you're not sure about something, don't hesitate to ask. That is not a problem at all. Just a quick shameless plug for those of you in our Central Queensland area, our upcoming Engineering Link project, which is for 10, 11s and 12 students, is coming up on June the 8th, later on this term. So there's information on our website for those in that area. I really encourage you to make that available to your students. What I'd like to do is just play this short video. Last year, this is our winner, Jamison. He was a year 12 student, and I asked Jamison some questions about participating, and I thought I'd just share this with you as a way to conclude that formal presentation part. Hopefully you can hear this.
Yeah, no sound.
Thanks, Mike. Yeah, I thought that might be the case. All right, so unfortunately it sounds not working, so I don't want to waste everyone's time by trying to find that, but this will be available to you in the presentation, as I said. So I will send this out and you can have a look at it, and if you think it's relevant or something you want to share with your students, then by all means feel free. I'd like to just, before we go to the chat and answer any questions that you have, I just want to again thank Mike and Hinu sitting in the background, running the webinar from the background for us. Hinu is also the person who puts out the call to arms for our engineers and as for all of our projects, and works really hard along with Stacey to keep us on the straight and narrow. But thank you, Mike, for your time. Hinu, thank you again from the background. I will turn my screen off and I will jump into the chat and see if there's anything there. But if anyone has any questions, oh, great. So Zane, apologies if I missed this. Are we aiming for a solid deck from end to end? No, Zane. It doesn't have to be solid, as long as we want it to have the intent of it being a bridge. So if it has small gaps as we work our way along, and you've just got some cross bracing and it looks like a deck, that is perfectly fine. It does not have to be solid. We're not actually going to get a Matchbox car and run it across the bridge. It's again the intent. Could a Matchbox car, drive across that bridge? Yes, or no. If there's gaps, that's not a problem. Hopefully that helps you. Too easy. Again, if you'd like to unmute yourself and ask the question, or you want to just type it in the chat, whatever works, I'm happy to go from that. But if you're done and you've had everything answered for you, and you're, we're more than happy for you to leave. First, is there a recommendation of how long you should spend working with primary school students, Thomas? That's a good question. How
long's a piece of spaghetti?
Yeah, exactly. About this long. To be honest, Thomas, it depends on the attention span of your kids. But I would say what I would probably recommend is teach them, is talk about and make the most simple deck you can, which would be the beam bridge, and just get them to try and, so the way they're going to build it, because the spaghetti itself is shorter than the distance, they're going to have to sort of do it in layers. So when they're building their beams, if they build their structures, don't make all of the joins at the same point for the layers of spaghetti that they work across. So, for example, if you have, like, if you look at my fingers in the picture, you want to sort of make one piece of spaghetti sort of that long and that one, so that when the joins are, they're not in the same spot. And then you try and make it as thick as you can. But in terms of how long you should spend, I think, particularly with primary kids, we would encourage you to just give them as much time as you can, but also provide as much structure as you can possibly give them, because then in most cases they're just going to go woohoo and put something together and hope. Yeah, they're not going to get up to the arches, I wouldn't think, unless you've got a particularly gifted group of primaries. Claire, if you make the bridge in advance, will this affect the strength, or is there a best way to store it? The driest place possible. If you, Claire, if you, I'm not sure where you're located, but there is opportunities we could, depending on where you are and things like that. I don't mind when the bridges are tested. They don't have to be tested in that time slot. So if, for example, if you're in a school that really wants to do the competition in term 2, even though the competition itself is in term 3, then I have no problem at all if you send your bridges to us, or if you're local, because I'm in Brisbane and we can work something out. I could come to you and test your bridges, and that can still form part of the competition. The competition is open now until August. We just happen to test in August because it's engineering week and it works well, and that gives people time to get there. But I'm more than happy to negotiate with you if you would like to do something sooner, rather than have to store them and then hope they last until August. But hopefully that answers your question. No problem, Ari, no problem at all. Bridge can build in sections. Absolutely it does. But the Estrie and Emery, the point is, though, that the spaghetti is not long enough to reach 35 centimetres, so you have to build it in sections. I'm not sure of another way. Mike, jump in if you think so.
No, what you explained before is, yeah, that the span is bigger than the standard piece of spaghetti, so you have to splice them together, but don't have multiple end-to-end joins located in the same spot. Try and overlap them and move it along, so it disperses the load a lot better. Yep. It doesn't create a weak spot, I should say, too.
So Kevin, to answer your question about, so Kevin's question is the hook and winch. So the hook itself is I'll send you a load hook. So all schools who have registered their interest so far will either have received or will receive, because I'll get that done by the weekend. Any I've missed up until the last few days, we'll send a load hook. What will then happen after that is, once you start getting into your competition and you've got a better idea of the number of hooks you're going to need for your school, then I will send you a number of those hooks. Separate category for primary school students, Miranda, no. Although we have in the past, so one of the location prizes is for primary only teams, but some years we get lots of primary, some we don't. So one of those location categories is a primary team. So yeah, so they could win the 150 if they don't win one of the top awards. Thanks, Tanya. Cool. Awesome. Thank you. Appreciate the feedback, everyone there. I won't read them out, but I do appreciate that. So yeah, does anyone have any final questions, either live or on chat? Because we're just about up to the 4:30, but more than happy to hang for a few minutes. But if we've answered your questions, then again, we really appreciate your time this afternoon, ladies and gentlemen. I know it's week 2 of a very busy term. We're all, how much glue is too much glue? Oh, sorry, I just noticed a question there from the Heatley team. That's again, as long as it's reasonable. I mean, some students will, like, all the way along the glue, as long as it doesn't look like they've taken the bridge and dipped it in a glue vat. We're pretty flexible in that respect. There's no way to actually know what's too much glue without looking at it and making a decision on that moment. But hopefully, if you look at the kids and they're just coating it and just painting it in glue, because the idea is we want the spaghetti to be the main structure and the glue is just there to support that, not the other way around.
Yeah. and some glues are quite heavy, so they could actually increase the amount of weight without you being fully aware of it, which will reduce how much spaghetti you can have, etc.
Good. Yeah, that's exactly right. Thomas, to answer your question, the total weight of the whole bridge, including the load hook. So once the bridge has the load hook in it, we then weigh it and we put on. So everything that's glue, spaghetti, and the load hook has to be 300 grams. It can be exactly 300 grams. That's not a problem, but it has to be that or less. See. Wait for some any last questions if there are any. But again, this for those who are still here, the recording will be made available in a week or so's time, along with the presentations. But again, looks like that's it from everybody. Thank you so much, everyone, for joining us. We really appreciate it. Best of luck with your bridges and your groups. Reach out if there's anything we can do to help you. Happy building, and we'll see you either sometime with your bridges. Thank you very much.